Hi, welcome to another episode on What the Fun Physics channel. So, this time it's going to be a little different. I don't start with a question, but then it's more of a story time. And if you're a student of mine, you know that I like telling stories. So, this is part autobiographical. The story goes like this. This was the summertime, and then we were learning optics, and this was back in 2012, I guess. So that's when I was in my second year, intermediate. And then my physics teacher was teaching us optics. And then he sort of asked us this question like, why do we find this hot water images on a sunny day? Like it's really hot and you're walking on the road, and then you suddenly know that there is this water image everywhere. We all know that it's nothing but an oasis mirage. Right? Why is this happening? Happen? Like, what makes it happen? It turns out as my physics teacher explained, like he gave us a problem to solve, and then when you solve it, you get to notice that what you're actually seeing is light from the clouds getting reflected. So it gets reflected, and then you see it. So what you're seeing is literally light which started here and then ending up in your eyes. So light is formed by this H2O in the clouds. What you see is water. So you see what as if water is coming from here. Imagine like that it's just like if you have a mirror, and if there is an image over here, let's say this is the real person you- over here, and if you're looking from here to see light from here, you would assume that the person is here, right? If you if there is a mirror and the light is coming from here, you would assume the object is here, even if the object is here. So it doesn't matter where the actual object is. What matters is in what direction the light is coming. Similarly, light is coming in this direction, so you would assume that it's actually water here. But the water was here. So what's exactly happening? Light when light is supposed to be straight line, right? So it turns out the answer is given by Snell's law. We all know Snell's law that medium changes, the light is going to bend, right? So on a hot day, what happens is all the hot air so will try to go up, and all the cold air will try to come down. But then you notice that as the hot air goes up and cold air comes down, sort of exchange happens, and you'll notice that the upper areas are all lighter. What you'll see is that all the cold ones will come down and all the hot ones went up. Why? Why is hot air down in the first place? Because the earth is getting hot and then it's heating up all the air over here, and all the hot air will go up. So it's all hot in the end, and this is all like cold relatively. That means this is lighter, denser, right? So as this happens, so what happens is light is going to go from one layer to another layer. So the temperature is changing, T is changing, which means density is changing. If density is changing, then refractive index will change. If refractive index changes, then light in a straight line, it starts to bend at each point. Instead of going like this here, so it will bend a little. And then this layer, instead of going like this, it will go bend a little. So on, it keeps on bending, bending, and so on. It reaches my eye. All this is okay. Why is the light in the first place? Like, does it make sense? So I asked my teacher, like, we know that there is this Snell's law thing and the light bends and all that, but why, sir? Why? Why does light have to bend when medium changes? Okay, so then he said that. So he drew something like this. He said there is a ball which is thrown into the water, and then you are playing with your cousins over there. When you're playing, uh, then suddenly one ball falls into the water, and then you ask one of your cousins to catch it, right? You want them to get the ball faster. So let's see that thing over here. So your cousin is here, the ball is somewhere in water over here, and then in order to get to the ball, there are multiple paths. One, like he can go directly straight, or he can, like this will take some time. As you know that he can go faster in sand and slower in water. He's not going fast and slow. Yeah, you might be thinking like we are discussing about light and what is this guy telling about all sand running and ball fetching and all that. Just bear with me, you'll see what I'm getting at. So what happens is like when you try to go there, so you know that so this path is not the fastest flying path, because like I can always choose some path like this, so that I run more along the beach and then run less in water. Since this going in water is slower for me, since I move slow in water, this path has to be smaller. So in water I have to travel less distance, and then in sand I have to travel more distance. That way I'll go from this point A to this point B in shortest time possible, right? So all I have to figure out is like out of all the paths, like one of the paths is that I go straight to this point and then come down. One of them is go here and then go here. There are multiple possible paths to go from here to here, and out of all this, if I try to calculate, like let's say here the velocity is v1 and here the velocity is v2, so I'll figure out that. So eventually try to find a minimum function. You know how to find minimum and maximum. I hope you do. So you'll find that there is a particular path like this, where this is angle theta 1 and this is angle theta 2. So uh, here one thing is here I go faster, here I go slower. So theta 1 will be greater than theta 2. That means in denser medium it bends more towards this side. So there is a particular path with this sort of configuration, and to be more specific, we'll figure out that we'll get a condition something like this, where v1, v2 are velocities in this and medium 1 and this is medium 2. Okay, so but this is all about a person trying to reach a goal. So all fine, and we end up with this formula. But what is this formula like this? I think we do. It's nothing but Snell's law, because if I just multiply this both with some c, this c by v1 is nothing but refractive index. Refractive index is speed of light in vacuum by speed of light in a medium. So this whole thing becomes refractive index. So this whole formula becomes n1 sine theta 1 equal to n into sine theta 2. So what we have arrived at is something really beautiful. You see, like somehow by taking up a person trying to go from somewhere in the sand to somewhere in the water, like with this changing medium and going from here to there, he is traveling along the path of least time. So the important word here is least time. So the person is trying to figure out a path to go from like somewhere here to somewhere here in least time, right? So this least time thing is very important. So the person knows that he has to go here to here, so he decides he has to go path. That's all fine. But here comes a bit of thing. So until now, I've asked my teacher what's with the oasis, and he said it's with light winds. And then I asked him why light winds. So he gave me this analogy of a person running in water, and then he told me that light always light always travels in a path of least time. Travels in. This is interesting. Now, okay, so everyone might ask you, light travels in the path of least time, so that may be fine. But the question is, if it's a person who is actually going from here to here, he knows where he's going. So he knows his future point, his destination. So since he knows his destination, he can optimize his path. He can calculate the most optimized path to go here. But for a light, how does the light know that it has to go to that particular point? Like, doesn't that seem weird, right? Like I have light source here and I have somewhere here where it reached. Let's say this is destination. Light could have gone somewhere here. Light could have gone somewhere here and here and here and many other points, right? Why did it choose this particular point as destination? And once it chose, how it knows it? So once the destination is chosen, I know that I can figure out this theta one and theta two. All this is fine because only particular theta one and theta two will tell me how to reach there in shortest time, right? So that's all fine. But in order to find this theta 1 and theta 2, I have to know that this is my destination. So that means somehow light knows its future. Somehow light already knows where it's going to go, right? So this was a little disturbing for me. Like I can't make sense of this. So then that's when I asked my teacher, like, why light go in a path of least time? Like, how does it know it's the future? So all he had told is that, okay, so he just asked me to be patient, and then that someday I'll reach a higher section or my BTech or bachelor somewhere, some professor would explain how this actually works. So I waited and I waited and I waited. This was me in 2012 with the question. And then somewhere in 2015, I had this course. Oh, actually in 2014, I guess, or early 2015, I guess. Yeah, so I took this course on optics. In optics, again, the same thing is repeated. And this, whatever I have explained, is called Fermat's principle of least time. Fermat's principle of least time. All this is fine. Then I asked my professor, like, why is this true? Then he said that not just light. So in 2012, I was thinking only light knows. But then in 2015, I was told that all the particles know. What I mean by that is that so all the particles actually travel along a path of something called least action. There is a term called action. this action term turns out to be so nothing but time for light. If I take some other particle, this action term would be something else. So there's a way to calculate it, and then what's interesting over here is there's this term called action. Action is nothing but integration of L and dt. What L is called Lagrangian. Lagrangian is nothing but kinetic energy minus potential energy. There's this term which we don't know why it's working. We don't really have a particular explanation. It turns out all the particles will go from point A to point A to point B along paths of least action. Okay? What is the path of least action? Like like if it was Newton, Newton would have killed this. The reason is for Newton, it's very simple. If there is a body and it goes in the direction of force acting on it, it doesn't matter. Like the destination doesn't exist for it. What exists is in this moment there is a force acting on the body, and the force will tell it where to go. But somehow it's the second way to deal with things, which is called action principle, which I'm talking about right now in this video, which is so mind bending and like so mind disturbing. So it talks about how like there is a first point and there is an end point, and then the path which any particle would take is a path of least action, like something in between, which will have the least s, okay, s minimum. It doesn't make sense, right? Like why would light any particle would know that this it has to go to the point. So this is still disturbing for me. But there is a really vague explanation of this given by one of my favorite physicists, Feynman. There is this super crazy Feynman guy who likes to explain things in a simple way. So what he says is that there is point A, which is the source point. There is point B, which is the destination. So what he says is that any particle actually goes in all the possible paths. So this is one path. This is another path. There is another path. There is a path which goes to sun and then comes back. So there is a path which goes to like a center of Milky Way galaxy and then again comes back. There are all these possible paths through which a particle can go and come back, which means that some of these paths take time more than so travels with the speed more than speed of light greater than c. What Feynman says is that reality all the particles take all these paths to go from A to B. None of them is so specific. It turns out each path has something called a phase. Okay, you know what a phase is? Like imagine there are two waves. Let's say I have a wave like this and then there is another wave like this. If these two waves meet at a particular point, you know that upside and this is downside, so they both cancel out. Similarly, this is down and this is up, they both cancel out. So if you have something like this, we have destruction. But if you have something like this and then something like this, what happens is these two waves will add up and just give me a bigger wave, right? Constructive. So this constructive and destructive thing depends on the phase difference. Phase difference is nothing but, let's say the top and top here, there is not much distance, there is very little delta x. But if you take the top point over here and the top point over here, there is a really big large gap. So whenever there is large gap, they will destroy each other. Whenever there is small gap, they construct each other. So he says, when one says that out of all these possible paths, most of the paths will cancel out their phases. So this will cancel out this one, the other one would cancel out other one, and turns out there is only one specific path for which this S is minimum, action is minimum, and which doesn't lead to much phase. Okay? And only the phase of this will remain. Everything else will cancel out. What Feynman technically saying is that all the parts and everything are actually going in all the possible parts, and then somehow, somehow only one of them is seen by us. It's like light is taking up all these things, but we are only seeing one of them. So I don't know how many of you find it really, like confusing, interesting, or whatever. But for me, it's still something to make sense of. So, as again, light somehow does know the future. Even particles knows its future. Only we here stuck in a loop just because Newton gave us this way of approaching life, and I don't know, it's stuck here. For me, if someone else actually makes sense of what's happening, please to tell me. So far, this is what I have understood, and then you know. So maybe if I have to end this video with one line, And that is like until now. So initially, I was thinking that physics often looks like nature is optimizing, but deeper down, what's actually happening is nature is not choosing; it is allowing everything and letting interference decide. By interference, I mean this constructive and destructive interference. And then, you know, I was thinking about least time, and then it sent me to something called least action. And then still this least action thing, like I thought it was all about knowing the future, but it's just that all the future possibilities cancel out, and only one of the future possibility will remain. That's what I would tell you. It's very simple. So I'll give an end line for you, which is all other possibilities, all other futures cancel out, only one remain. So this is how physics works. I don't know if it made sense to you, but then this is the story I've been carrying on for so long. I just wanted to put it out. So if you like this video, do like this video, subscribe, and maybe comment too. Thank you.